So everything that we've talked about so far has been valence bond theory, VB theory, and that includes hybridization of the central atom to give sp, sp2, sp3, stuff like that. It is really great for describing the bonding in most molecules, and it does a good job if you're just like sitting around in a coffee shop, like I said earlier. You don't need fancy computers or anything like that for valence bond theory. But now we're going to look at, honestly, what is a better theory. It's called molecular orbital theory. And molecular orbital theory was built upon the quantum mechanical wave functions we talked about in chapter 3 in order to, and expanded then for molecules. So they take what was already complicated math and essentially make it even more complicated, which is crazy. And you might think, why would anybody want to do that? Well, valence bond theory is certainly not perfect. We're going to see that it doesn't do a very good job to talk about magnetism. So molecular orbital theory will be much better about talking about paramagnetism, and molecular orbital theory will actually talk about color better. We're not going to talk about that as much, but it does. And it does refer to the bonding a little bit more accurately than valence bond does. In molecular orbital theory, or MO theory, atomic orbitals are delocalized into molecular orbitals. So on the right-hand side is a molecular orbital diagram for dilithium. And if you're a Star Trek fan, hopefully you got excited just like I did just now. Dilithium was the energy source that the Starship Enterprise used to go to warp drive. Now, dilithium is a real compound, which is pretty cool. However, I don't think it can be applied towards warp drives. Darn it! But maybe one day, et cetera, et cetera. Anyway, don't worry about that. If you look on the molecular orbital diagram, on the left side, you have a lithium atom. And lithium, if you remember from chapter 3, is 1s2, 2s1. And that's what you're seeing like straight above it. Like here's the 1s2, here's the 2s1. Each electron, one spin up, one spin down, et cetera, et cetera. On the far right side, you see a second lithium atom, which is also 1s2, 2s1. So on the left and the right-hand side of molecular orbital diagrams, you often see the atomic orbitals. And then in the middle right there, all this stuff in dark blue, those are the dilithium molecular orbitals. And we'll talk about that here in a little bit. But it's important to realize that the left and the right-hand side, those are just atomic orbitals. And then it's the middle part, that's where these molecular orbitals are, the orbitals that form between the atoms. In a molecular orbital diagram, you'll have bonding and anti-bonding orbitals, and they're both important, and we'll talk about this. Bonding, you can probably imagine, makes the molecule stronger. Anti-bonding makes the molecule weaker. Unfortunately, MO is pretty complicated. I'm talking very, very complicated. And people talk about like quantum computing and stuff like that. Hey, that's where MO theory is great for it, because there's a lot of things that have to be calculated in order to get good results at. So one day, I hope my students will have what I call the TI 2000 calculator, and it'll be like the ultimate calculator, and you can put stuff in and blah, it'll spit out all these molecular orbital diagrams. Oh, I can only imagine. However, not quite there yet. The TI 2000 that I want to see anyway hasn't come out yet. So in Chemistry 221, we're going to look at very simple kind of versions to see how this works. And we're going to look at only diatomics, which are two atom systems. And we're going to look at diatomics only from the first and second periods. So this isn't going to be a huge example set we're going to look at, but here's what's going to happen. We'll look at two atom systems. So we can look at, say, O2, and we can look at H2, but we won't look at things with three or more atoms. So for example, NH3, ammonia, and H2O, those have too many atoms. We won't look at them, unfortunately. We're going to look just at simple diatomics. And also, we're going to look at atoms only up to neon. So we'll look at things between hydrogen and neon, but we won't look, for example, at chlorine, Cl2, because that's third period, or bromine, or any of those kind of examples. So we're going to get a good sense as to what MO theory offers, and one day in another course you might then look at more sophisticated examples, and you can use this knowledge then to help make sense of what you're seeing, stuff like that.
Nitrogen is not magnetic. It is diamagnetic. All the electrons in the molecule are paired. Oxygen, however, interacts with a magnetic field because it is paramagnetic. This physical property indicates that molecular oxygen has unpaired electrons. Molecular orbital theory accounts for this fact, but valence bond theory does not.
If you look in the upper right-hand corner, this is the Lewis structure for O2, all right? And if you look at the Lewis structure, there's a double bond between the oxygens. Each oxygen has two sets of lone pairs, 4 electrons total. If you think about formal charges, the formal charges of oxygen are 0, all that kind of stuff, which is great. But if you look at it, all of the electrons are paired, like each up has a down. Each of those is a pair of electrons, either a lone pair or a bonding pair. And you don't have any electrons by itself. And that's interesting because in the real world, as we saw in that video, oxygen sticks to magnets. It's paramagnetic. So it has odd electrons hanging out, kind of doing its own thing. And that's not what we see in the Lewis structure. Now, the Lewis structure, VSEPR geometry, valence bond theory, they all predict that O2 would be diamagnetic. And in reality, O2 is very paramagnetic. So you can see right away then there's some problems with the valence bond theory. It's really good for most of the things, but it's not perfect. By the way, valence bond does a great job with dinitrogen, N2. When you do its Lewis structure, everything's diamagnetic, and nitrogen goes through the magnet no problem. But there are some issues, and oxygen is a classic example of where the valence bond theory kind of breaks down. So let's look at molecular orbital theory and see how it can predict the paramagnetism of O2. There's a couple of principles of molecular orbital theory that help as you go through this stuff. And some of these are pretty obvious, but I just want to go through them. So first of all, in science and chemistry, there's a big thing about symmetry, and this applies here. So what that means is that at the number of molecular orbitals you have equal the number of atomic orbitals that you put into it. So you're not going to create or destroy any orbitals. So for example, if you're going to make H2, each hydrogen has one 1s orbital. So two 1s atomic orbitals mean that this H2 molecule will have 2 molecular orbitals. On the other hand, for lithium, the dilithium thing we saw earlier, each lithium had a 1s and a 2s orbital, so each of them had 2 orbitals, 2 atoms and 2 orbitals each, that's 4 atomic orbitals. And the molecular orbitals that came out of it also have 4 molecular orbitals. So all the atomic orbitals you put in equal all the molecular orbitals that you put out. So here's a question you might see. If you combine 2 oxygen atoms, and remember each oxygen is 1s2, 2s2, 2p4, if you have 2 oxygen atoms that you combine to make a molecule, how many molecular orbitals will you expect to have? So what you need to do to answer this question is figure out how many atomic orbitals are on each oxygen. Well, the 1s is an atomic orbital, the 2s is an atomic orbital, so that's 2. But 2 p's, if you remember, 2 p's break up into x, y, and z. So each p orbital has 3 orbitals total. So that means there's 1 plus 1 plus 3. Each oxygen has 5 atomic orbitals. And since there's 2 oxygens, that's 10 atomic orbitals that we're putting in. So we would expect to have 10 molecular orbitals that come out. So the 1s, the 2s, and the 3 2p's on each oxygen combine to make 10 molecular orbitals. That's kind of the idea happening. Remember that p's have 3 orbitals, d's have 5 orbitals. If you had an f, it would have 7 orbitals, but we're not going to look at d's, f's, or anything like that. We're only going to look up to the 2p's in this section because of the limitations of what we're doing.
The bonding molecular orbital has greater electron density in the bond region. The anti-bonding molecular orbital has reduced electron density in the internuclear region.
When you combine atomic orbitals together, you have 2 possibilities. One of them makes the molecule stronger, and those are referred to as bonding orbitals. So in that kind of lower video right there, that showed when the 2 1s orbitals came together to make a strong bond, and that's a bonding orbital. On the other hand, you can have those same 2 1s orbitals combine, and in an unfriendly method, a method that makes the molecule weaker, weaker. And those are called anti-bonding orbitals. Now, both of these are basically head-to-head overlap of the atomic orbitals. So they're both given the same symbol sigma, but notice that the anti-bonding gets a sigma star. That star means that it's an anti-bonding orbital and it's not as strong. Now, the reason for bonding and anti-bonding goes back to wave theory, which is something you might see in physics. If two waves can combine, they can create a stronger wave. This is constructive wave interference, sometimes they call it. It makes for a stronger one. That's where the bonding comes from in molecular orbitals. On the other hand, you can have two waves combine in destructive ways, and that creates, basically cancels out the wave. And this is where the anti-bonding comes from. So when two atomic orbitals come together, you're going to have a bonding one, which makes the molecule stronger, and you're going to have an anti-bonding one, which makes it weaker. Principle number 2 then says that when you have bonding and anti-bonding molecular orbitals, that's because the two atomic orbitals create two molecular orbitals, all right? And one of them is lower in energy, it's the bonding molecular orbital, and the anti-bonding molecular orbital is higher in energy. That does not make the molecule stronger. The third principle just says that as you start applying electrons to these molecular orbitals, you always start at the lowest molecular orbitals and work your way up to the highest molecular orbitals. And in chapter 3, we talked about Pauli exclusion principle, how every electron needs its own set of quantum numbers. In this world, Pauli exclusion just means every electron has to be different from the other electrons, and we'll talk about that. Hund's rule is the rule that said that each electron gets its own orbital first, and you only pair up when there's no more room left to do anything else. And we'll see examples of both of this as we go through and we assign electrons.
In contrast to valence bond theory, which assigns bonding orbitals to individual atoms, molecular orbital theory assigns the orbitals involved in bonding to the entire molecule. The simplest illustration of molecular orbital theory can be seen with the hydrogen molecule. According to molecular orbital theory, the 1s atomic orbitals of the two hydrogen atoms combine to give two molecular orbitals. Because atomic orbitals are wave functions, they can combine either constructively or destructively. Additive or constructive combination of the two atomic orbitals gives a bonding molecular orbital, while subtractive or destructive combination of the two atomic orbitals gives an anti-bonding molecular orbital. The bonding and anti-bonding molecular orbitals formed by the combination of two 1s orbitals are called sigma 1s and sigma star 1s respectively. The bonding molecular orbital, sigma 1s, is lower in energy than the original atomic orbitals. And the anti-bonding molecular orbital, sigma star 1s, is higher in energy than the original atomic orbitals. Like atomic orbitals, molecular orbitals can accommodate a maximum of 2 electrons each, with the electrons in the ground state occupying the lowest possible energy orbitals. The molecular orbitals in the hydrogen molecule can be represented with lines or boxes placed at the appropriate relative energy levels. The 2 electrons in the hydrogen molecule both occupy the bonding molecular orbital. Because most of the sigma 1s bonding molecular orbital is located between the 2 nuclei, electrons in this orbital draw the 2 nuclei together by electrostatic attraction. The sigma star 1s anti-bonding molecular orbital consists of 2 lobes. The majority of the space occupied by the 2 lobes does not lie between the 2 nuclei. In this molecular orbital, the region between the 2 lobes is known as a node. Electrons in this orbital would actually draw the 2 nuclei apart by electrostatic forces. Hydrogen has no electrons in this anti-bonding molecular orbital.
Okay, a lot of information in that video, but that's a great overview of how to build the H2 molecular orbital. So let's try and break that down a little bit and see what's happening. So at the beginning of the program there, it showed the atomic orbitals of hydrogen. And again, on the far left and the far right, that's where the hydrogen atomic orbitals are. So this is a hydrogen atom on the far left, and this is a hydrogen atom on the far right. And initially, they each have a single electron because they're 1s1, okay? And when you make a molecular orbital then, 2 atomic orbitals in make 2 molecular orbitals. The lower orbital is the bonding molecular orbital, and they call it sigma 1s because it came from 1s orbitals. But the lower bonding has to be countered by a higher anti-bonding molecular orbital, and that's called the sigma star 1s, and that destabilizes the molecule. There's actually no electrons between the nuclei, so that's going to basically break the bond. So that's building the molecular orbital diagram. And now to assign electrons, you have a total of 2 electrons to assign, one from the first hydrogen and one from the second hydrogen. And you literally just start putting them in the lowest molecular orbitals first and go up. So in this case, the 2 electrons both go to the sigma 1s molecular orbital. And you can see how one is spin up and one is spin down, so they each have their own quantum signature, which is Pauli exclusion principle. And there's no electrons in the anti-bonding sigma star 1s molecular orbital. So this is the molecular orbital diagram for H2. And you can probably see that there's going to be more electrons in the bonding than the anti-bonding. So that makes it a more stable version than the individual hydrogen atoms that come together. We'll talk about that in a little bit. But if nothing else, remember earlier I talked about how there are have no fear of ice clear brew, the 7 diatomics. Hydrogen is one of them. And that's why hydrogen is almost always H2 and not just H, because there's an energy savings, if you will, making the H2 molecule relative to the H atoms. Now, for dihelium, you would have a helium atom on the left and a helium atom on the right. They both have 1 atomic orbital, so we're going to make 2 molecular orbitals then. One will be lower, that's the sigma 1s orbital. That doesn't show it in the picture, but that's the sigma 1s there on the bottom. And the sigma star 1s, the anti-bonding molecular orbital, is on the top. Now the difference between helium and hydrogen, helium has 2 electrons. So on the first helium atom, you could draw 2 electrons for that one. And on the second one, you could draw 2 electrons for that one. So we have a total of 4 electrons to place in the molecule. And like before, we'll put them in the lower orbital first, the bonding molecular orbital, and then we'll put any left over in the anti-bonding. And as you can see, since we have 4 electrons, the first 2 go in the bonding sigma 1s, but there's also 2 electrons in the sigma star 1s. So dihelium has just as many bonding as anti-bonding molecular orbital electrons. And we're going to see that makes the molecular orbital for He2, dihelium, not very attractive energetically. Instead of just thinking about maybe it's good or not good, let's talk about a way to quantify if you make a molecule or not. And scientists do this with what's called bond order. And for molecular orbital theory, bond order equals 1/2 parentheses the number of bonding electrons minus the number of anti-bonding electrons. If you have a bond order that's greater than 0, that means that it's a stable molecule, and that molecule should exist. However, if you have a bond order of 0, and in higher applications you might see even a bond order that's less than 0, but we're not going to talk about those all mean that you have unstable molecules, and the molecule should not exist, all right? So bond order, if it's greater than 0, that means it's going to happen, it's going to exist. So in dihydrogen, if you remember, we had 2 sigma 1s electrons and no sigma star 1s electrons. So bond order for that, 1/2 parentheses bonding minus anti-bonding. This would be 1/2 parentheses 2, because there's 2 electrons there, minus 0, because there's no electrons there. 1/2 parentheses 2 minus 0 parentheses 1/2 of 2, bond order 1. This is a stable molecule, and you bet H2 exists. Most hydrogen exists as diatomic hydrogen. It's rare to have hydrogen atoms unless you're like on the surface of the sun or in a lab or something like that. Now, dihelium had a different molecular orbital diagram. It had 2 electrons in the sigma 1s and 2 electrons in the sigma star 1s. So notice it has just as many bonding as anti-bonding electrons. Well, you can do a bond order analysis for this as well as for hydrogen. And again, if that bond order is greater than 0, the molecule exists, but if it's equal to 0 or less than 0, it's not going to happen. So in dihelium, bond order equals 1/2 parentheses bonding minus anti-bonding parentheses. So in this case, that's 1/2 parentheses 2 minus 2, 1/2 of 0 equals 0. That's unstable, and we would not predict the dihelium molecule to exist. And I don't believe that dihelium has ever been made. There's no reason for it to be made energetically. There's no energy savings, if you will, having that happen. So dihelium does not exist. So bond order will be really useful to us as we figure out how these things go. Now, in the Lewis structure, there's an equivalent idea for bond order. And I have up here just a molecule, acrylonitrile. And I like this molecule as an example because you can probably see there are single bonds, there are double bonds, and there are triple bonds. And so in a Lewis structure, if you have a single bond, that's a bond order 1. So if we calculate a bond order of 1 in molecular orbital theory, that corresponds to a bond order of 1, a single bond in Lewis structures. And likewise, in a Lewis structure, a double bond would be bond order 2, and a triple bond would be bond order 3. And this can be pretty important. We're going to see that as bond order goes up, your bond length goes down. So the bond order 2 double bonds are shorter, tighter together than bond order 1 single bonds. And triple bonds are even shorter than double bonds. And molecular orbital theory has all these same kind of things. So a bigger bond order means tighter, smaller bond length and stuff. It's pretty cool. We'll talk more about this as we go through the class, but that's the equivalent idea of a bond order in a Lewis structure versus molecular orbital theory, which is what we're doing right now. This is a question you might see. What is the carbon-oxygen bond order in formaldehyde? Formaldehyde is CH2O, the structure's there on the right, and we want to know what the bond order is between the carbon and the oxygen. Well, you can see in that Lewis structure that between the carbon and the oxygen, there's 2 lines. That's 2 bonds, a double bond. And bond order of 2 is what a double bond means. So every time we see a bond order 2 in molecular orbital theory, you can think about that as a double bond in a Lewis structure. Same thing. The carbon-hydrogen bond order would be 1 because it's a single bond. If you had a triple bond, it would be bond order 3, etc., etc. The fourth principle of molecular orbital theory states that atomic orbitals will combine to give molecular orbitals only when the atomic orbitals are of similar energy. And this principle is why we're not talking about things past neon, by the way. But anyway, here's some ideas. If you have a 1s and a 1s atomic orbitals coming together, going to give you a great molecular orbital. But a 1s atomic and a 2s atomic orbital, not going to give you very good molecular orbitals because they're so far apart from each other. They don't mix very well. Now, 2s plus 2s is great. 2s plus 2p doesn't do a good job. 2p plus 2p would be great, but 3s and 2s doesn't give very good ones, etc., etc. So we're only doing up to neon because that's 2p plus 2p, 2s plus 2s, and 1s plus 1s. When you get past neon to chlorine or bromine or iodine or any of these other ones, then you start to have lots of mixing. So like maybe 3p and 4s would start to mix, and the molecular orbitals get much more complicated, and this is where computers can really help out. So anyway, that's why we're keeping it just up to neon, and this is great examples, but realize as you get into other classes, then you may have to deal with this other kind of mixing that's going on. So here's a question. What combination of atomic orbitals would you expect to create the best molecular orbitals? And again, the punchline is you want them to be as close to each other as possible. All right. And you can see that 1s plus 2p, those aren't even close to the same. 2p plus 3p, not even close. But 3d plus 3d should give pretty good molecular orbital mixing. And this is what happens with transition metals, by the way. A 4d plus 4f isn't going to happen. 5G, which is hopefully an orbital type that's coming but isn't here yet. It needs no molecular orbitals. Well, conceivably it would. That's not a good answer either. Anyway, hopefully the idea is that if they're the same kind of orbital, they'll mix well. If they aren't the same kind, then you may have to use computers to see if they mix at all. By default, I'd say they probably wouldn't mix real well unless those n numbers are bigger. This is the molecular orbital diagram for dilithium once again, and we can now kind of understand a little bit more about what's going on. So on the left-hand side, you have lithium number 1. On the right-hand side, you have lithium number 2. And then in the middle is the actual molecular orbital diagram for the dilithium molecule. So lithium is 1s2, 2s1, and you can see those gold kind of arrows. That's what that represents on both the left and the right side. And then in the middle, we have the molecular orbitals. 2 atomic orbitals make 2 molecular orbitals. One's lower in energy, the bonding. One's higher in energy, the anti-bonding with the star. So notice we have sigma 1s followed by sigma star 1s, then sigma 2s followed by sigma star 2s. Well, the 1s electrons combine to make 2 sigma 1s and 2 sigma star 1s. And those aren't super exciting for us. However, on the top part, the 2s atomic orbitals will combine in the lower one there to make 2 molecular orbital sigma 2s orbitals. So if you want to know if this is stable or not, we can use that bond order definition, 1/2 parentheses bonding minus anti-bonding. Now all the lower ones are the bonding ones. There's 2 bonding ones there and 2 bonding ones there, so that's 4 bonding. And we also have 2 anti-bonding there, and this one is empty, so there's 0. So it's 1/2 parentheses 4 minus 2, bond order 1. This is a stable molecule. So dilithium does exist. Darn it, it doesn't run the Starship Enterprise yet, but maybe one day, you never know. But it's kind of fun for me as someone who's really into Star Trek to think about stuff like that. Diberyllium would be 2 beryllium atoms, and beryllium has 1 more electron than lithium. So beryllium is 1s2, 2s2. And if each beryllium is 1s2, 2s2, you can probably imagine that when you have an extra 2s electrons, they're going to go in the anti-bonding orbital. And so just like with dihelium, diberyllium is going to have just as many bonding as anti-bonding electrons. It's going to have a bond order of 0, so we would not expect diberyllium to exist. Draw it out if you want to. It's a totally cool exercise. But dihelium, diberyllium, probably not going to happen because they have a bond order of 0. When you get to boron, this is our first atom that we've seen with 2p orbitals. And remember, when you have a 2p orbital or a 3p or 4p or anything like that, each of them has 3 atomic orbitals. There's like a 2px, a 2py, and a 2pz. So because we have 2 atoms coming together, they're each going to have 3 2p orbitals. That means there's going to be 6 molecular orbitals in this part. And what happens when those 6 molecular orbitals come together for the 2p, they end up making 2 sigma and 4 pi molecular orbitals. Now the sigmas, you're going to have a lower bonding sigma and a higher anti-bonding sigmas, and the pi's, you're going to make 2 lower bonding pi bonds and 2 higher anti-bonding pi bonds. So it's kind of weird. So there's a little bit more of a pattern here, but it is a pattern that can be predicted. Unfortunately, though, there's a little bit of a catch, and it depends on where you are in the periodic table where this catch becomes relevant. So in this point now, I'm going to refer to NBC and also, as we'll see in a little bit, phone, F-O-N-E. Now, NBC refers to atoms with boron, carbon, and nitrogen, NBC. And when you have 2 atoms coming together that are NBC, they have the pi bonding ones lowest. Those are those right there. Followed by bonding sigma, then followed by anti-bonding pi, and antibonding sigma pi. Now notice that the pi's, there's two of them, and sigmas only have one. So if you go from lowest to highest, it creates what I will sometimes refer to as the 2-1-2-1 pattern. That's two pi's followed by one sigma, followed by two antibonding pi's and one antibonding sigma. This is what you'll use for molecules that have nitrogen, boron, and carbon. So for example, N2 will use this, or B2, or you could also have things like CN when the two atoms come together. But if you have N, B, and C molecules come together, you want to use the NBC diagram. This 2-1-2-1 is what happens when it starts to plop out. Now, the orbital diagrams become more complicated. You can start using core or core electrons in square brackets to represent the 1s interactions. And this is similar to the noble gas notation we used. So for example, boron's atomic electron configuration is 1s2, 2s2, 2p1, but you could write that as helium in square brackets, 2s2, 2p1. If you write for molecular orbitals core or core electrons, that represents the 1s interactions, and I'll show you some examples of that here in a little bit. This is for NBC, but there's also oxygen, fluorine, and neon. So those three have a different thing, and I'll show you that example in a little bit. This is an example of diboron. So diboron, when you do its configuration, each boron is 1s2, 2s2, 2p1. Now notice here the core. Its 1s isn't even showing because the 1s on the left and the 1s on the right will cancel each other out, so it's no big deal. So 1s2 is just shown there under core. Then we have 2s2 and 2p1. That would be the three electrons in the orbitals. But the right-hand side is the same. It's another 2s2, 2p1. So when you combine the atomic electrons into molecular orbitals, you can see how the sigma 2s and the sigma star 2s are canceling each other out, and that's very normal. But what's interesting is that the two 2p electrons, one 2p on the left and one on the right, they go into the pi 2p orbitals there, the lowest part of the 2-1-2-1 NBC interaction. So one electron each is going to give it some cool properties, but that is the diboron molecular orbital configuration, which is pretty cool. So the sigma 1s and sigma star 1s are both filled. Then you have sigma 2s2, sigma star 2s2, and pi 2p has two electrons inside it. There is another set of orbitals, though, as we said. There's also the oxygen, fluorine, and neon. So I'm going to refer to these as phone, F-O-N-E. And when you look at the phone orbitals, now the sigma is lowest, followed by the 2 pi bonding, and the pi star, the two of those follow, and sigma star follows that. So notice it's the bonding orbitals that flip, the anti-bonding orbitals stay the same. So while NBC had a 2-1-2-1, the phone orbitals are 1-2-2-1, sigma first, followed by the 2 pi's, then pi star, then sigma star. So it's only the bonding orbitals that flip when you go from NBC to phone. And again, I'm just the messenger here. I know this is a little weird, but it's all stuff you can do. As before, core electrons in square brackets can represent the sigma 1s interactions, and that'll save you some time as we go through here. This is the molecular orbital diagram for dioxygen. Now again, down here in the bottom, the core electrons, that would be the 1s interactions. Oxygen, the atom, is 1s2, which isn't showing, 2s2, 2p4. So it's 1, 2, 3, 4. And the right-hand side oxygen would be the same way. 1s2 doesn't show, 2s2 does show, 2p4. So the two 2s electrons combine with the other two 2s electrons. The first two go in the sigma 2s, fills it up. Second ones go in sigma star 2s, fills it up. Good to go. But the excitement is in the upper part. And remember, it's 1, 2, 2, 1, sigma, pi, pi star, sigma star. You have a total of 4 electrons on the left and 4 electrons on the right. That's 8 electrons. So 2 of them go in sigma 2p, 3, 4, 5, 6 go into pi 2p. And finally, 7 and 8 go into pi star 2p. And by the way, this is Hund's rule we're seeing. Each electron gets its own orbital first, and you only pair up if there's no more room. So in Hund's rule, notice that each electron gets its own box first. This is the molecular orbital diagram for O2. And again, it's got 1, 2, 2, 1 instead of 2, 1, 2, 1, which is important. Why this Hund's rule becomes important is that it helps to explain the magnetism. And notice there how in O2, in the pi star 2p, each electron had its own orbital. And you don't start putting them together until there's no more room. So if you had one more electron, it would fill up the first box, and another electron would fill up the other pi star 2p box. So because O2 has those two unpaired electrons, that means that it's paramagnetic. Paramagnetic things are attracted to magnetic fields. So we talked about earlier how the Lewis structure for O2 doesn't show any paramagnetism for O2. But boy, oh boy, when you see this molecular orbital diagram, you focus on that part that I circled right there. Those two individual electrons are not paired up. So O2 is paramagnetic. It's attracted to magnetic fields. And this is one of the real powers of molecular orbital theory. It does a better job talking about the structures and reactivities of molecules than Lewis structures do. Now, nitrogen, dinitrogen, N2, first of all, it's NBC. So it's going to have 2, 1, 2, 1 in the 2p interactions there, and that's what we see. But when you figure out the electrons, each nitrogen is 2p3, so the molecule would have 2 of those 2p3s, or 6 electrons. So you'd put the first 4 into the pi 2p, and the last 2 electrons in the sigma 2p. But notice here how every up electron has a down electron. That means that N2 is diamagnetic, and it is. In the video we showed earlier where oxygen stuck to the magnet, nitrogen went through first, and it just went through like no big deal. So molecular orbital correctly predicts that not only is N2 diamagnetic, but oxygen is paramagnetic. That's why we're seeing differences with the magnetic fields. Here's a question that's actually a lot easier to answer with molecular orbital theory than it is regular valence bond or Lewis structures theory. And it says, is N2 plus paramagnetic or diamagnetic? Well, in chapter 3, when we took away an electron to make a cation, a positive ion, you took it away from the highest orbital that was still available. And honestly, in molecular orbital theory, it's the same way. So if we wanted to make N2 plus, we can start with neutral N2, which is the molecular orbital diagram that's showing right now. And N2 plus, we would remove one of the electrons from the highest occupied molecular orbital, the sigma 2p orbital. And by removing one electron, we would then have one electron that was up or down without its corresponding opposite. So N2 plus is paramagnetic. You can easily predict the magnetism of molecules and stuff of ions using molecular orbital theory. But even better, it's really cool for making both positive and negative ions, which is another bonus of molecular orbital theory. So this leads us into making ions, all right? And if you do make an ion, either a positive cation or a negative ion, what you always want to start with, at least I would recommend, is making the neutral version first and then add or subtract electrons. So if we wanted to make, for example, O2 plus, we would start with neutral oxygen. And neutral oxygen has, you could write the core electrons. It would have sigma 2s and sigma star 2s, and each of those would have 2 electrons. And then as we saw earlier, oxygen neutral is sigma 2p, pi 2p4, pi star 2p2. There were 2 unpaired electrons. But O2 plus 1, we're going to remove an electron from the highest occupied molecular orbital. So remove one of the electrons from the pi star 2p, and either box is fine, it doesn't matter. But lo and behold then, you still have an unpaired electron. So O2 plus 1 would be paramagnetic. It still has an unpaired electron. Your bond order goes to 2.5 1.5 if you figure it out, which is kind of cool too. So you can do the ions and stuff using molecular orbital theory very, very readily. Once you have the neutral atom or molecule, then you can just add or subtract as necessary. O2 minus 1, you would again start with neutral O2. And the diagram for neutral O2 had the core. It had sigma 2s, sigma star 2s, both of those with 2 electrons. Then it had sigma 2p2, it had pi 2p4, and originally it had pi 2p2. So each of those boxes had a single electron. But if we're going to add electron, we're going to add electron to the lowest unoccupied molecular orbital. So if we're going to add an electron, you want to add to either of those boxes. Doesn't really matter. In this picture, they added it to the left, and that's fine. You could have added to the right, no big deal. You add it to the lowest empty spot possible. So in this case, O2 minus 1 is also paramagnetic. It's got the one unpaired electron, and when you calculate bond order, it comes out to be 1.5. So again, making positive or negative ions from these is really simple once you have the neutral version. You just add or subtract to the appropriate place, and you're good to go, and you can predict magnetism, bonds order, all that kind of stuff. After a while, it gets to be a drag writing molecular orbital diagrams. When you're learning, it's important. And for the lab we're going to do, I want you to use the complete molecular orbital diagrams. But after a while, you can start using what's called shorthand notation. And this is a lot easier to complete and to represent molecular orbitals than you would have otherwise. Now, on the left-hand side is the complete molecular orbital diagram for N2. And we talked about how it has 4 electrons in pi 2p, 2 electrons in sigma 2p. And again, this is NBC, the 2121, because it's 2 nitrogen atoms. The NBC, the N is the nitrogen. Anyway, if you wanted to write this as a shorthand notation, first of all, you start off by writing core electrons. You can also write just core in square brackets, but make sure you put that down. And then what you do is you put the different types of molecular orbitals in parentheses, and you use a superscript to represent how many electrons there are. So if you look at this part right here that I just circled, that's the sigma 2s molecular orbital. And in those parentheses, it's sigma 2s, and there are 2 electrons in sigma 2s. That's the superscript. So again, you have to be very formal with this. Don't try and cheese out. All right, you have to have parentheses around the molecular orbital, and then a superscript representing the number of electrons. So for N2, that would be sigma 2s raised to the power, if you will, of 2, then sigma 2s2, pi 2p4. You don't have to separate pi 2p into x and y for me, but you can if you want to. I wouldn't. But anyway, pi 2p4, and then finally the last one, sigma 2p2. And you put them in order of increasing energy, i.e. bottom to top. All right, don't do it any other way. But this is a nice shorthand way that you can actually write in Microsoft Word or something and convey to your colleagues then what you're doing. This is a question you might want to know. What's the bond order of N2 plus? All right. And N2 plus is going to be like N2, where we have the shorthand notation version at the bottom without one more electron. So N2 plus is going to be like N2 neutral, which is listed right there. But N2 plus, of course, has one less electron. That's where the positive part comes from. And that electron is going to come from the highest occupied molecular orbital. So that's going to be taking away one of those electrons. So instead of sigma 2p2, it's going to have sigma 2p1. So bond order equals 1/2 parentheses bonding minus antibonding. And you can use just the top orbitals or the whole thing. Whatever you want to do is fantastic. But in this case, if you take just the top orbitals, you have 4 bonding plus 1 bonding, 5. There are no antibonding electrons to the right of this. So it's like 1/2 parentheses 5 minus 0, 2.5 is the bond order, which is kind of a cool thing to do. Now, you could have included the 2s interactions. You would have 1/2 parentheses 7 minus 2, which would give you 2.5. And if you wanted, you could even include the 1s interactions. That would be 1/2 parentheses 9 minus 4. But either way, you're going to get 2.5, so you decide what is best for you. You can determine the number of sigma and pi bonds in a molecular orbital diagram, just like you can find the number of sigma and pi bonds in a Lewis structure. So we've seen in the shorthand notation that there's both sigmas and pi's being used. So if you want to find the number of sigma bonds, just use the sigma orbitals. So number of sigma bonds equals 1/2 the bonding sigma minus anti-bonding sigma, and the number of pi bonds is equal to 1/2 the number of pi bonding electrons minus anti-bonding pi electrons. And if you've done it correctly, the overall bond order will equal the sigma plus pi bonds, and this is the same as in Lewis structures. For N2, all right, here's the shorthand notation again. The sigma 1s and sigma star 1s are included in the core. But notice I have green electrons and orange electrons. The green electrons are the sigma electrons. They come from sigma orbitals. And in this case, the pi electrons are the gold ones. The anti-bonding pi there is empty, so there's nothing up there, just like the sigma star is empty. There's no sigmas there. So bonding for sigma would be 1/2 the bonding, the no star version, minus anti-bonding, the starred version, 1/2 parentheses 4 minus 2, 1 sigma bond. Pi bonds are similar, 1/2 parentheses bonding pi minus anti-bonding pi. There's 4 bonding pi, and the pi anti-bonding pi is empty, like we said, 1/2 parentheses 4 minus 0, 2 pi bonds. And if you combine the number of pi bonds with sigma bonds together, 1 sigma plus 2 pi equals bond order 3, and lo and behold, that's the bond order that you're going to have there too. I have an extra pi there. Sorry about that. I'll take that out in a future version, but you hopefully get the idea. So remember, sigma plus pi equals bond order, and that's a nice way to kind of check yourself. This shows the trends of going from B2 to Ne2, the 2p interactions. And again, notice on the left-hand side, you have the NBC diagram, 2, 1, 2, 1, where the pi's are first, sigma is next, pi star and sigma star. But the right-hand side, those are the FONE, the phone ones. They're 1, 2, 2, 1. The sigma is first, followed by the 2 pi's, 2 pi orbitals. Then the 2 anti-bonding pi's follow that, and the sigma star follows that. So it's kind of a cool thing that happens. You can also see, for example, the bond lengths in that little thing in the bottom. They start off fairly large with B2. They get smaller as you get to N2, and then they start getting bigger as you get to F2. Dineon doesn't exist, so that's why there's really nothing there for it. So that's kind of the idea. Also notice the magnetism, how B2 and O2 are paramagnetic, even though the Lewis structures probably wouldn't include that. You really should have the core electrons for all of these interactions. Don't just assume they're not there or something. That is important, but it's not a big deal.
When light strikes an object, part of the light is reflected. In the eye, electrons in rhodopsin move from a pi bonding orbital to a pi anti-bonding orbital. One of the molecule's double bonds turns into a single bond, allowing rotation. The double bond then reforms, and the molecule locks into a new shape. The change in shape triggers a nerve impulse, and we perceive light.
This is a pretty cool application of molecular orbital theory, and by you looking at that red rose in that picture, you've used molecular orbital theory in your body. Anyway, I get excited by weird things, I know. But anyway, in your body is a compound called rhodopsin. And again, this is way beyond my biology knowledge, but rhodopsin allows you to see red. It creates a signal that goes to your brain that says that's red. And rhodopsin has a double bond. And so when you see red, the light comes in. It has just the right amount of energy to break that pi bond, but what it really does is that it takes one of the pi bonding electrons and promotes it temporarily to an anti-bonding pi orbital. So it goes from the pi to the pi star. And double bonds don't rotate, but single bonds do. So the rhodopsin is rotated to this meta-rhodopsin, the other version, and that allows that electron in the anti-bonding to relax back to the bonding orbital. And as that happens, that sends an impulse to your brain, which says, hey, you're seeing red. Oh, pretty cool kind of stuff. Anyway, this is what molecular orbital theory really rocks, and it's going to be so cool one day. Got to get the computer power a little higher and stuff, definitely, but one day I think we're going to use molecular orbital theory to answer a lot of questions, and especially now that AI is becoming so prevalent, I think AI combined with molecular orbital theory will have a lot of really cool applications for society. Okay, that's it for Chapter 5. I appreciate you being here, and I hope this has been useful as you continue your studies in this area. If you have questions on anything, of course, you can let me know. There are more resources for you to learn this material, and you can always talk to me if you have any questions. All right, thanks again for your time for being here. Good luck with your studying, and have a great day.